Welcome to Colligative Properties of Electrolyte Solutions. So, if we have an electrolyte, that means that we have ions in solution. If we have ions in solution, that means that the molality of particles in solution is not the same as the molality of the compound that we have in solution. So if we have, say, sodium chloride, if we have 1 molal sodium chloride, that 1 mole of sodium chloride is going to dissociate into 2 moles of particles. 1 mole of sodium ions and 1 mole of chloride ions. So this means that the colligative properties, the osmotic pressure, the boiling point elevation, and the freezing point depression, will depend on the total particle concentration, which is not the same as the sodium chloride concentration. So you need to be careful if you have some ionic substance that's going to dissociate in solution. So remember that our freezing point depression for a solution depends on the molality of dissolved solute particles. So the freezing point depression of 0.100 molal of glucose in aqueous solution. Glucose is not ionic, so it will remain together in the molecular form. Remember that delta T is equal to Kf(m). So Kf there is the freezing point, the molal freezing point depression constant of whatever our solvent is. In this case it would be water. The M solute there is the molality of our solute. The molality of glucose is 0.100 molal. So the freezing point depression constant for water is 1.86 degrees Celsius per molal. So degrees Celsius times kilograms divided by moles, and multiplied by 0.100 molals. And I've already changed that from molality into moles per kilogram. So note here that our moles cancel and our kilograms cancel, and we're left with degree C. So in this case, with this concentration of glucose, we get a freezing point depression of 0.186 degrees C. Now, this is the depression, which means that that's the change in temperature. So water started out freezing, pure water freezes at 0 degrees C. We're going to drop the freezing point by 0.186 degrees C, and that means that the freezing point of our solution will be negative 0.186 degrees Celsius. But the freezing point depression of 0.100 molal sodium chloride in aqueous solution is not 0.186 degrees Celsius. It is, in fact, double that at 0.372 degrees Celsius. And this is because the sodium chloride is dissociating into sodium ions and chloride ions in aqueous solution. So the total solute particle concentration is 0.200 molal. And the only thing that matters in our calculation for freezing point depression or osmotic pressure or boiling point elevation is the molality of our solute. Doesn't matter what our solute is, doesn't matter what the identity of our solute is, which means if we essentially have a solution, we have one solution that is 0.100 molal of sodium ions, and in that same solution we also have 0.100 molal of chloride ions. So the total dissolved particle concentration is 0.200 molal. So when we calculate the colligative properties of electrolyte solutions, we need to be very careful to take into account the number of particles, in other words ions, that will be formed in solution after formation. So for sodium chloride, you get 2 ions for every formula unit that dissolves. For something like lead 4 nitrate, if that were to dissolve in water, you'd get 1 lead ion and 4 nitrate ions out of solution, or into solution rather. And so the total solute concentration is 5 times the lead nitrate, the lead 4 nitrate concentration would be. Okay, so you need to be very careful if you have an ionic compound that you need to figure out what the concentration of each ion is in solution. So that was colligative properties of electrolyte solutions.